Hello?
Hey, Matthew.
Hello?
Yeah, can you hear me okay?
Hey, sorry. Yeah, can you hear me?
Yeah, I can. Before we go on today, let's just revisit this problem before last time, where we're trying to find the arc length of this function from y equals -2 to 2. I had some problems with it the first time because I didn't quite get how they had done it. In other words, they gave us this function right here, okay, which means y is x to the 1/3. And if you plot that, you get this. And if you were going to do the arc length of this, you'd do it from -8 to 8. dy dx. The problem is it gives you this vertical tangent right there, and your calculator is going to cough when you go to put that in. When you use the nint function, do you know how to use nint?
Yep, the integrate it.
Yeah, the numerical integration. Well, if you try integrating this function over here, your calculator is not going to like it because it's going to cough when it gets to that vertical point there. According to my book, it's liable to do anything, but you can't trust the answer. If you integrate a function that has a vertical tangent in between the things, you can't integrate it. Well, the reason I got confused on this is because even if you write it as a function of x, it still graphs like that. There's no getting around it. Whether you write it as a function of y or a function of x, it graphs with that vertical tangent. However, if you think about inverses, and we were to plot the inverse of this, it's going to look like this over here on the right. Now, notice what they did, or I got this out of the book. They actually, instead of plotting the inverse, they just switched the x and y axis. Okay? Now, we can do this just fine by doing dx dy, which is 3y squared, and going from -2 to +2. And this may be one of the first times I've ever seen them switch the axis like this, where they make the horizontal axis y and the vertical axis x. Well, that's not really what they're doing. Let's look at it properly. What they're really doing is taking the inverse of this function, because we know the inverse is going to be the same length, right? The inverse is a line that is a reflection about y equal x. And so even if I use my standard coordinates and I take the inverse of this function, it looks like this. And now I've got a function where I can find the arc length. It's going to be the same arc length as this because it's the same arc. And only thing is I have a horizontal slope there which doesn't cause any problems. So I can go ahead and differentiate it. And when doing arc length, you got to be a little careful about that. In other words, because they give you two choices, you can either do dy dx or dx dy, you have to use some criterion to differentiate which one you're going to use. And it's usually based on stuff like this, where if you do it one way, you have a vertical tangent, and if you do the inverse, you do not. So, alright, I just wanted to straighten that out.
Alright. So what again is your email? I just got a new phone, so I forgot your email. It's David Cutman at
David Cowan, here, I'll write it right here. 1949 at gmail.com.
All right. I believe I just sent you the first one.
Okay. They're completely different than these 4 pages you sent the other night?
Yeah, this is a different review that we got yesterday.
Okay. Because there was a lot of material in that other stuff that we didn't cover yet. That's fine, whatever keeps you current. What's the current stuff on? Is it arc length or something different? Surface area, probably?
Yeah, it'll be arc length, surface area, because it's just a review for the test and stuff like that. Right, there you go. Now my phone remembered you, so it'll send. Yeah, it's easy.
Haven't gotten it yet. You sent it to this email? Ah, I just got it.
Oh, there we go.
I just got it. It always takes a little bit. Just one problem?
Yeah, then I sent more. They're coming.
Okay. Let's look at this one. Okay. What are we going to do here?
It looks like we just need to figure out the equation.
Well, what do we know? We know that the 16x to the 6th is what?
That's the curve itself.
Isn't that dy dx squared?
That's the slope.
That's dy dx squared. And we know it's dy dx because of that dx right there. That always has to match the denominator. Okay, so what is dy dx? If dy dx squared is 16x to the 6th, then dy dx is what?
Yeah, it would just be 4x cubed plus 1.
Yes. Okay, so now we know dy dx. Let's come up with y. Integrate. In other words, if the derivative is equal to this, then we're looking for the antiderivative of that.
Okay, so that would be x to the 4th.
Yep. So that's the function we're looking for. Now, let's go back a moment. It's actually x to the 4th plus c, correct? So there's our function, and they do give us an initial condition. If the curve contains the point 1, 4. So if 1, 4 is on this curve, that allows us to solve for c. Plug that into this equation and we'll have c.
Alright, so it's going to be 3.
So the real equation is y equal x to the fourth plus 3. That's the answer they're looking for. A.
All right.
Okay? That's a good question. I like that question, but you just have to proceed through it step by step, knowing what you know.
Mm-hmm.
Running out of room on my desktop here. Oh boy, from 0 to y, huh? A curve is given by the equation that it's the integral of that. So, Jesus, this material isn't hard enough that they feel a need to trick it up. That's what gets me.
Right.
I mean, do you agree?
Yeah.
I mean, really, couldn't they just give us regular problems? They gotta, it's like the Rubik's Cube of arc length. Well, the way I'm going to approach this is I know we need dx dy. Right? Let's assume, we know that with arc length we need to find either dx dy or dy dx.
Mm-hmm.
Well, in this particular case, I can find dx dy pretty easily. The fundamental, if x is equal to the integral from 0 to y of this function, the fundamental law of calculus says that if we're going to take the derivative of x, in other words, if we're going to take the derivative relative to y, it's equal to that function. So dx dy is equal to the square root of 9y squared plus 6y. That's the truth. The fundamental theorem of calculus has two parts. That's part one. And it's dependent on going from a constant to a variable. And if it goes from a constant to a variable, and you take the derivative of an integral, no matter what the variable is over here, it becomes the function as a function of y. Second part of the fundamental theorem of calculus says that if you take the integral of a function, it's equal to f of b minus f of a, right? In other words, this is the one we're very familiar with. That's how you evaluate any integral. You take the antiderivative of the function, you evaluate it at b, and you subtract the antiderivative evaluated at a. So there's part two, and there's part one. And it's worth your time to memorize those and know what they mean and represent, because they just give you too many questions regarding the fundamental theorem of calculus. But that being the case, we know what dx dy is. So if we're trying to measure the curve from 1 to 5, well, now it becomes a simple problem. we're going to go from 1 to 5, the square root of 1 plus dx dy squared dy. Well, what's dx dy squared? 9y squared plus 6y. Now we have an integral that, interestingly enough, you can do without a calculator. Are you supposed to not be using a calculator in these?
Yep.
Okay, notice, first of all, there's not many of arc length problems that you're going to be able to solve manually. Merely because when you take the second derivative of a function and you add 1 and you take the square root of it, you don't get something that is very easily integratable. They gave us something quite special here to make it very easily integratable. Notice that that's 9y squared plus 6y plus 1 dy. Well, 9y squared plus 6y plus 1 happens to be 3y plus 1 quantity squared.
Okay.
So that the square root of this squared, I can get rid of the exponent and the radical sign, and now I just have to integrate that. What's the integral of that?
So that would be 16 minus 4.
Well, let's integrate it first before you plug in.
Oh, yeah, duh.
Add 1 to the exponent and divide by the new exponent.
So it'd be 3 halves y squared.
Plus what? What's the integral of 1?
X plus y.
Y. So now that's the integral of that function, and we're going to evaluate it from 1 to 5. How do I do that?
You just do plug in the 5 for the both y's and then subtract when you plug in the 1's.
So that's the plugged in the 5's, and when I plug in the 1, I get 3 half plus 1. And this parentheses is very important. You're always subtracting when you evaluate an integral, right? If you don't use this parentheses, you're going to get the sign wrong on this number right here. Okay, so this is 85 halves minus, well, 3 halves plus 1 is 5 halves. So minus 5 halves equals 80 halves equals 40. Whew. Boy, I didn't see that 40 at first, and I looked at B through E, and I said, I know 40 is the answer here. If there's any problem I know how to do, it's this one. Okay. Again, I don't know that you could do this problem if you didn't know the fundamental theorem of calculus. You have to know that x prime is equal to the square root of 9y squared plus 6y. Basically, you have to know that the derivative of an integral is the function. All right, let's look at number 9. Now, let's see. Force equals, work equals force times distance. this one a second. Seems fairly straightforward. The information they're giving us is that 10 newtons, which is a measure of force, is required to stretch the spring 8 centimeters. So the force is going to be 5/4, and we should be able to plug it into the same equation, so the work done stretching that force of 5/4 times 12 centimeters should be 15. That's awfully linear. There was no calculus involved there at all. Let me just check. There's an example of this in the book. Oh boy, my other book. Just want to make sure I'm not missing something here. I think I've done it right, but like I said, I'm always suspicious if there's no calculus required.
Yeah, they said for the answer for 9, it says D, 90.
Ah, okay, good. I mean, I'm glad I'm looking it up then. Because obviously it's not linear like I made it out to be. Alright, compressing a spring. Alright, I got a problem here that's an example that should clarify the issue here. Let me just go through this example and this will help, and then we can go back and look at that problem. So this problem says that the force of 750 pounds compresses a spring 3 inches from its natural length of 15 inches. So natural length is 15 inches, compressed 3 inches. Find the work done in compressing the spring an additional 3 inches. Solution. By Hooke's law, the force required to compress the spring, oh, I see why it's not linear. Because as you compress a spring, the force required to compress it is not the same. It's dynamic. It changes. It's the harder you compress a spring, the harder it is to compress it further. Or if you stretch a spring, the harder it is to stretch it further. So F is not constant like I treated it when I did it. So if F of X is equal to K times X, which is the equation we want to use to compress a spring. Yeah, that's what I was leaving out the first time. Hooke's law, we need that equation. F equals K times D, or in this case, K times X. So they're saying that to compress it 3 inches equals K times 3, and to compress it 3 inches is 750. So K equals 3 divided by 750 divided by 3. So K equals 250. Okay. So our equation is F of X equals 250X. And
They had, so the answers.
yeah, we'll get there.
Alright.
All I want to do is show you for certain how to do this problem because I'm reading it out of the book, and then we'll go and we'll look at your problem.
Oh, okay. I was a little confused there. All right.
Yeah, no, I understand why. I was a little confused on the problem. I haven't done a work problem stretching a spring for a while, so I needed to kind of refresh myself on it. But to compress it, in other words, this is the function right there. So to compress it from 3 to 6 inches, it's already compressed 3 inches. I'm going to compress that function to 50x dx. And that's the amount of work that's going to be required. Okay, and that is relatively easy to do. So now let's look at your problem. So in your problem, we have f equals kd, or if we want the function f of x equals kx, we know that f of x is 10 to stretch it a distance of 8. So k equals 5/4. So our f of x function equals 5/4 x.
X. All right.
And how much work would be done in stretching the spring from its natural length to 12?
Should be from 0 to 12?
I don't think so. I think we need to go, it might be the same, but I think we need to go from 8 to 12, which is the amount of additional work, and then add it to 10 newtons, and we'll have the total amount of work required to go from 0 to 12. See the difference? It might be the same answer, but I'm not sure it's going to be. I don't think it is, actually. In other words, if I do this, that's going to give me the amount of work required to stretch that spring from 8 to 12. Well, that's going to allow us to get an answer to the problem because we know how much work it takes to go from 0 to 8.
Oh, okay.
So we're just going to add it to that. Okay, well, what's the integral of that? 5/4 x squared divided by 2. So 5/8 x squared evaluated from 8 to 12. You want to do that?
Yes, if you plug in 12, it'd be, well, you can pull out the 5/8, right? Since it's just a
Yes, it's
coefficient.
Yes, so I can pull out the 5/8, put parentheses around it, and I got 144 minus 64.
All right.
Which is 80, which means this whole thing is 50. So it takes 50 newtons to compress it from 8 to 12. It took 10 newtons to compress it from 0 to 8. 60 should be our answer.
Yeah.
Is it?
9 is, 9 they say 90.
They said 90?
Yeah.
All right, let's go back and integrate this thing from 0 to 12 and see if that matters. Thing is, I'm not sure. Let's see. So from 0 to 12, I guess it's the same thing except 0 to 12. So it's 5/8 of 144. Eight goes into 144 16 times, and that's how they got 90. Wow.
But it's weird that way we did wouldn't work.
It is weird. Especially since the way I did it is the exact example in the book, where it asks you how much work to additionally compress it a further 3 inches.
Yeah.
So I did it exactly the way they did it in the book, only their question was find the work in doing an additional compression, which I did. It was 60. And since they told us work in doing the initial compression, or it was 50, and so 60 should be right, but going from 0 to 12 gives you 90. Well, I'm a little confused, to be honest. In fact, the example in my book says that notice you do not integrate from 0 to 6 because you were asked to determine the work done in compressing the spring an additional 3 inches, not including the first 3 inches.
Mm.
Where this question's a little different. It says how much work's done in stretching it from its natural length to 12. God, that still seems like it has to be the same answer. And it's not. That's a puzzler. I'm not sure what the, I mean, I trust that their answer is 90, although it's not impossible for them to have done it wrong. They basically did it from 0 to 12. I'm not sure that's the right way to do it.
Mm-hmm.
I'm inclined to think that the way we did it is a better way, figuring out how much additional work is required, doing from 8 to 12, and then adding it to 10. Now I get it. Now I get it. There wasn't 10 newtons worth of work done stretching it from 0 to 8. It was a force of 10 newtons. They never told us how much work was done stretching it from 0 to 8.
Oh.
Yeah, exactly. So we didn't know how much work was done in the first 8 centimeters. However, knowing the force was 10 newtons allowed us to come up with the equation, the formula of stretching this spring, and then to figure out the total amount of work, we do want to go from 0 to 12. So I get it completely now. I misread. For some reason I was thinking newtons was a measurement of work, and it is not. It's a measurement of force. Work is force times distance. So now I get it perfectly. Yeah, this was quite different than the example in the book that I looked at. All right. Did you send me anything more?
Yeah, I think so.
Got to find a spot on my desktop to put this thing.
Mm-hmm.
So many calculus sessions in a row here that I have all this calculus material that I want to keep handy. Tell you what, I'd like to tutor nothing but calculus. I don't know how to do that though. All right, the base of a solid is bounded by y equal tan squared of x, y equal 4 minus x squared, x equals 0 in the xy plane. Each cross section perpendicular, let's just, what does y equal tan squared look like? Now, are you allowed to use calculators at all on these to even see?
Yeah, this one is a calculator one.
Looks like, just so I can kind of get an idea. It's always nice to be able to draw a picture. Oh, sure, and they're not going to graph it for me. Oh, there it is. So, let's see. Do we have any... This is pi over 2. And the other function is 4 minus x squared. That is an upside down parabola that's been vertically shifted up by 4. And was that 4 minus x squared? Yeah. Something like that. Okay. You see how I graph that? In other words, y equal x squared is this. Y equal minus x squared is that. Y equal minus x squared plus 4 is the bottom one shifted up by 4.
So what region are we doing?
I'm sorry? What?
So we're doing a little triangle sort of region?
Yeah, let me look here at the rest of the problem. I was just graphing it. Each cross-section perpendicular to the x-axis is a rectangle with one side in the xy plane whose height is 2. What's the volume of the solid? So it's a rectangle perpendicular to the x-axis. So we're looking at rectangles like this.
Oh wait, yeah, there's that one.
That come out from the board at a height of 2. I'm not a very good artist, but you can kind of get an idea there.
Uh-huh.
Okay? So, first of all, let's talk about figuring out the area of that rectangle. Because we're going to take the area of each rectangle, we're going to multiply it by the thickness of the rectangle, and the skinny side of this rectangle is the x-axis. So it's dx. In other words, it's always worth trying to figure out what the skinny side of your object is. In other words, it's got a base that is the distance between these two functions. It's got a height that's a constant 2. And it's got a thickness of dx. So we're going to integrate the area is 2 times the difference in the functions. And this function is on top. So it's 4 minus x squared minus tan squared of x. This bottom function is tan squared of x. This top function is 4 minus x squared. So the base of the rectangle, or the width, is this function minus that function. In other words, as we move from 0 to the right, and we're going to evaluate it from we evaluating it from 0 to this intersection point? Or are we evaluating it from all the way over here?
I think because it says it's bounded by the x equals 0, so it's bounded by the y-axis. So we do 0, 2, and I'm going to find that intersection right now.
Ah, there you go. X equals 0. So you're right, it's bounded by the y-axis. So we're looking for the volume of that right there that I've circled, correct?
Uh-huh.
Okay. So we know the function we're going to integrate, and we know it's going to be a dx. So we're going to go from 0 to this intersection point. How do we get that intersection point?
I graphed it, and it's 1.041044. 1.041044.
Okay. And you graphed it by putting in a y1 and a y2 and finding their intersection?
Yep.
Okay. Do you know how to do NINT?
Yep.
We could actually do that manually if you want to practice. It's not that hard. Notice that the integral of tan squared is, it is that hard. The integral of tan squared isn't so easy.
Right, 1, and then...
Yeah, Yeah, that might require net.
Comma 0.
Now, there's a special way you can do net using y1 and y2. You know how to do that?
Yep. So I got 3.12. That's not on there. Oh, I didn't multiply by 2.
So you had y1
6.24. 3. Yep.
y2
We'll say D.
x comma
0.
comma 1.041. Okay, that's what you did?
Yep. But then I also have to multiply it by 2. So then that's what I got.
So what's the right answer? C?
D, because it's the 0.243.
Okay. Oh, multiplying it by 2 because of the height.
Yeah, I forgot that.
Yeah, I did too, actually. That was outside there. So, okay, cool. Let's look at 11. Let me just graph this real quick, just to make sure there's no points in there that are not differentiable.
Is that a function that I can type in on the calculator that'll do that for me, or no?
And we can do this one by hand, I think. Maybe, I don't know. Let's set it up and see if we can calculate. I don't see any points on there that are not differentiable. So we should be able to take dy dx, square it, plug it in. What's dy dx?
dy dx would be, so you subtract, how's that going to hold the x going down and you subtract 1 from the exponent?
Mm-hmm.
So it's 2/5.
So we're going to have the integral of 1 minus y prime squared dx, going from -1 to 1. Y prime is that, so y prime squared is 4/25 x to the -6/5. So if I plug that in for y prime squared, I get 4/25 x to the -6/5. Can you do a nint on that?
Yeah, I'll do that.
Notice that when I squared the x to the -3/5, I just multiplied it by 2. I didn't square the exponent.
Minus.
There is a problem here. No, I graphed it for a reason. There's the graph of it. What's the problem going to be?
It says, oh, hold on.
This right here.
Yeah, because when I graphed it, it said it was valid or whatever.
Well, notice that we graphed the function they gave us, which was y equal x to the 2/5, but you can't take the derivative of that across from -1 to 1. It's not differentiable at this point right here, 0. It's got a cut. So the way we're going to have to do this is by differentiating it from -1 to 0 and then adding that to the derivative from 0 to 1 of the same function. If you do all of this with NINT, you might not get that answer. Because
I didn't get an answer. It didn't tell me.
Ah, okay. So it coughed when it did that right there. So try doing it from -1 to 0. See if you get an answer. It should be relatively easy to change the NINT function. I can do NINT and Wolfram Alpha also if you want me to. I can see that it might be a little tough to put that in the NINT.
Non-real answer.
What's that?
It says non-real answer.
Non-real answer. Let me put this in to this. Wow. Let's see. See if I can figure out how to do it. Okay, so we're going to take the NINT of 1 minus 4 divided by 25 times x raised to the minus 1.2 comma minus 1 comma 0. Let's see what it thinks I wrote there. The beauty of Wolfram Alpha is it'll give you feedback so you'll know whether you put in the right thing.
Don't just go with it.
That looks right, doesn't it? No, it doesn't have the square root of it. So I need the square root of it. So if I put another paren right there, oops, and another paren right there, and this one I want to raise to 0.5. That's right, isn't it?
Looks right. Yeah, I couldn't do it. I didn't do it right enough calculator.
I mean, that's what I have written here. If I go from, let's see what happens to Wolfram Alpha if I go from -1 to 1. Let's see if it coughs due to that 1 point. And notice how much longer it's thinking. Standard computation time exceeded, meaning that it ran into that problem. So here's our answer going to be. So going from -1 to 0 gives us a length of, I don't like that imaginary part, but standard length exceeded also. Well, I'll take the real part. And then let's go back and do it from 0 to 1. Well, I tell you what. With the free Wolfram, you don't get much time. Try again with additional computation time. Oh, you got to pay.
What?
Start free pro trial. Wow. Can you do that on your calculator? Or can you figure out whether you got it put in right or not? Put it in like this. The only difference for your calculator is you need X after the last paren. Not after the last paren. In other words, right there. You need to have a comma X like that.
I'll try it out.
if you put it into your calculator exactly like that, you should get an answer that we can add to that 1.468. And according to my diagram, it looks like it's a longer interval.
You said not a real answer.
All right. Well, I think it is a real answer. The only reason I think it's real is because they're giving us the visual depiction of it. There's the function, and the area under that curve is the answer. So whatever the area under that curve is what we want to add to the length from -1 to 0, which I'm pretty sure is this 1.468. So I don't know how to do it, though. I could try it on my calculator. I won't have time today, but I'll put it into my calculator and see if I can't get a number for that. So at least we can figure out what the answer is here. The answer is supposed to be 3.031. Makes sense. That means that my part of the curve is going to be 1.57. which is a little longer than 1.468. So, but, I mean, this problem looked overly simple when we first looked at it, right?
Yeah.
And the reason it wasn't simple is because of that cusp at 0. So you have to get around that by doing two integrals. You've got to integrate from -1 to 0 and then again from 0 to 1. And that'll definitely solve it.
I think how she does it is she changes it when you're not integrating X anymore, you're integrating Y. Like you saw, it's weird. That makes it look weird.
I don't think that's going to work with this. This was not a vertical tangent. That's what we had to do with the very first problem we talked about today, was to consider its inverse, which had a horizontal tangent rather than a vertical tangent. But this doesn't have a vertical tangent. This has a cusp. So even if you were to take the inverse of this function, you're still going to have a cusp. And you're still not going to be able to differentiate beyond that cusp. So I don't know. There may be a different way to do it, but I'm quite certain that the best way to do this is to do it in two pieces from 0 to 1 and from -1 to 0 and then from 0 to 1. Because after all, that has to be the length of the curve, right? I mean, it doesn't matter how many times you chop it up. All right. So let's see. We have another session tomorrow?
Yep.
I think it's in the afternoon, like at 5 or something. 6.
Yeah, I think maybe 8. I don't know. I think it's later.
Okay, and we'll be working on the same set of problems? No, we've worked on all 3 of them so far. So you're going to send me more?
Yeah, I just have, I think tomorrow I have a free response, 2 free responses, and then also another packet that I don't know.
We got plenty of work.
Yeah.
So we're not going to go back to these 4 that we were working on the other night? Because we never finished those. Okay, I'll put them away then.
All right.
Okay, I will talk to you tomorrow, Matthew.
All right, bye.
All right, bye-bye.